The cosmos is defined by scale, but no world in our immediate celestial neighborhood embodies the concept of sheer grandeur quite like Jupiter. As we look outward from our fragile blue outpost, we find a planet that operates on a scale so vast, so turbulent, and so extreme that it challenges the very limits of our planetary physics. This is a comprehensive look at the supreme monarch of our solar system, an in-depth script exploring the monumental scales, the crushing physics, the dramatic temperatures, and the violent history of Jupiter. To comprehend Jupiter, we must first confront its staggering, mind-boggling mass. In the realm of celestial mechanics, mass is the ultimate currency, dictating gravity, holding moons in thrall, and sculpting the very fabric of local spacetime. Jupiter is not simply a large planet. It is a gravitational powerhouse that contains more than twice the mass of all the other planets, dwarf planets, asteroids, moons, and comets in our solar system combined. It sits at roughly 1.898 times 10 to the 27th power kilograms. To translate this colossal scientific figure into something relatable, Jupiter is approximately 318 times more massive than Earth. During the dawn of our solar system, some 4.6 billion years ago, a massive cloud of interstellar gas and dust collapsed to form our Sun. After the newly born star swept up the vast majority of the nebula's material, a planetary disk remained. Jupiter, forming first and fast, acted like a cosmic vacuum cleaner, aggressively sweeping up the lion's share of the remaining hydrogen, helium, and cosmic dust. Because it claimed so much of the leftover material, it grew to such a size that it behaves like a miniature solar system, holding at least 115 moons in its orbital grip as of 2026. Yet, for all its terrifying mass, Jupiter is a gas giant, which means its density is surprisingly low. Its average density is only about 1.33 grams per cubic centimeter. This is just slightly denser than liquid water, a stark contrast to the rocky, metallic density of Earth. Because it consists almost entirely of hydrogen and helium gas, the very same ingredients that make up our Sun, it is often referred to as a failed star. Had Jupiter accumulated roughly 80 times more mass during those chaotic early days of solar system formation, the immense gravity would have crushed its core with enough pressure to ignite nuclear fusion. It would have flared to life as a red dwarf star, transforming our solar system into a binary star system and painting our skies with two suns. This colossal mass is packaged inside an equally astonishing volume. Jupiter's physical dimensions are hard to visualize from our terrestrial perspective. It possesses a mean radius of about 69,911 kilometers, meaning its equatorial diameter stretches across roughly 142,984 kilometers. If Jupiter were a hollow sphere, you could pack more than 1,300 Earths inside of it. When compared side by side, Earth looks like a tiny marble resting next to a massive basketball. However, despite its immense volume, Jupiter is spinning at a rate that defies its size. While Earth takes 24 hours to complete a single rotation, Jupiter completes a full rotation on its axis in a blistering 9.9 hours. It has the shortest day of any planet in our solar system. This rapid, high-speed spin generates immense centrifugal forces. Because the planet is not solid but rather a fluid mix of gases and liquids, this rapid rotation causes the planet to bulge outward at its equator and flatten at its poles. The equatorial diameter is significantly wider than the polar diameter, a physical phenomenon known as oblate spheroidal flattening. This hyperrotation is also the driving engine behind Jupiter's iconic striped appearance. The planet's outer atmosphere is sheared into violent, counter-rotating jet streams. The lighter-colored stripes we see are called zones, which are areas where warm gases are rising upward from deep within the interior. The darker bands are called belts, where cooler gases are sinking back down into the depths. These belts and zones rub against each other at speeds exceeding 400 miles per hour, creating chaotic boundaries of extreme turbulence, swirling eddies, and storms that can last for centuries. Because Jupiter is so massive and possesses such a gargantuan volume, its gravitational influence is felt across millions of miles of empty space. If you could somehow descend through the swirling clouds and stand on a hypothetical surface where the atmospheric pressure is equal to Earth's sea level pressure, you would experience a gravity that is 2.52 times stronger than Earth's. A human weighing 150 pounds on Earth would instantly weigh an agonizing 378 pounds on Jupiter, their muscles, bones, and cardiovascular system buckling under the crushing downward pull. This gravity acts as both a shield and a threat for the rest of the solar system. For billions of years, Jupiter's immense gravitational field has acted like an orbital bouncer. It deflects incoming comets and asteroids, hurling them safely out into interstellar space or dragging them into its own atmosphere to be swallowed up, protecting the inner, rocky planets like Earth from catastrophic impacts. However, this same gravity also destabilizes the orbits of nearby space rocks, occasionally flinging them inward on dangerous trajectories toward the Sun. As we plunge deeper beneath the visible cloud tops, the concepts of gravity, mass, and volume converge to create some of the most hostile environments imaginable. Jupiter does not have a solid surface like Earth or Mars. If you fell into Jupiter, there would be no ground to break your fall. Instead, you would experience a continuous, never-ending descent through an increasingly dense and hot atmosphere. At the outermost edge of the Jovian atmosphere, temperatures are bitterly cold, hovering around a freezing -108 degrees Celsius. Here, clouds of ammonia ice and ammonium hydrosulfide drift in a thin, freezing mist. But as you sink deeper, the sheer weight of the thousands of miles of gas above you begins to exert a crushing pressure. This pressure acts like a piston, compressing the gases and causing the temperature to skyrocket. A few thousand kilometers down, the pressure becomes so extreme that the distinction between gas and liquid disappears entirely. The hydrogen gas transitions smoothly into a hot, dense fluid. Deeper still, at depths of around 20,000 kilometers, the pressure reaches millions of times that of Earth's sea level. Under these mind-bending conditions, hydrogen atoms are squeezed so tightly together that their electrons are stripped away, allowing them to flow freely. The hydrogen becomes a liquid metallic state. This ocean of liquid metallic hydrogen is completely unique to gas giants. Because it conducts electricity, the rapid rotation of the planet stirs this metallic fluid into a swirling, churning dynamo. This dynamo generates a magnetic field of terrifying proportions. An invisible magnetic bubble that is 20 times stronger than Earth's and stretches millions of kilometers into space, trapping lethal radiation and bombarding Jupiter's closest moons. At the very center of this massive world lies the core. For decades, planetary scientists debated whether Jupiter possessed a solid rocky core or if it was simply gas all the way down. Thanks to gravity measurements taken by NASA's Juno spacecraft, we now know that Jupiter likely features a fuzzy, dilute core made of heavy elements, rock, and exotic ice that has partially dissolved into the surrounding liquid metallic hydrogen. At this deepest point, the temperature is estimated to reach a blistering 24,000 degrees Celsius. This is hotter than the surface of the Sun, fueled by the slow, continuous gravitational contraction of the planet's immense mass. So this is Jupiter. Subscribe for more and thanks for watching.